Hello, nurse scientist. Welcome to Unit 3, as it takes us into the wonderful, quantitative, wacky world of data. Numbers, formulas, and procedures. Oh my! But do not be alarmed, because the whole goal is just for you to become savvy in understanding key terms, what to look for as you are reading research studies, and also kind of what to know when you begin to conduct your own research studies. And the thing to know there is there are a lot of statisticians out there that will be available to help you when you create your own research study. So just know that, and know that this is a focus on quantitative research designs. And remember that research designs are like house plans. It's your blueprint for action. And page 150, table 9.1, is fabulous with some key design features for quantitative studies. And the design options are listed there as well. So let's focus on quantitative research because it is all about causality. That's really what quantitative research does. It's seeking to look at cause and effect. Increased caloric intake equals increased weight. Well, I know that. And basically, causality really says that things have causes, and causes lead to effects. But not all quantitative studies examine cause and effect. So, that's where sometimes people get confused. Because sometimes these quantitative studies will simply describe a variable or examine relationships. But causality is really at the root of quantitative research. And so our research questions that are a part of every quantitative study will guide our design. And that's just how we're going to build our house, how we're going to do our research. And it includes things like buying the right size couch for your living room. Those are important things. And here's some criteria for the causality that we're looking for in quantitative research. For example, a causal study examines the effect of a specific pre-op education program on length of stay. Well, we know there are many factors that affect length of stay. For example, diagnosis, age, surgery, type of surgery, complications, etc. So to determine the causality, it's really important to design the study so the effect of a single cause, for in this case, the pre-op educational program, can be examined apart from the other factors affecting length of stay. Because you really don't want it to be age or a type of surgery that affects the length of stay. You want it to be pure, that you're looking at that educational program. See? Isn't that cool? So, research designs will vary in their ability to support the criteria to make causal inference or implications. So, our experimental designs really offer the strongest evidence of whether a cause, an intervention, results in a certain effect. And as you recall, experimental designs are more rigid and controlled, like in a laboratory setting. And this is really why they are highest on the evidence hierarchy chart, because they are so controlled for all those extraneous variables, and so you're trying to get to the pure truth. So let's review for a minute about experimental design. Now, the characteristics of a true experimental design include the following. The intervention. This is where the researcher will do something like an intervention or a treatment. And this intervention is manipulated. Now, manipulation is a form of control. And it is most common in experimental and quasi-experimental designs. For example, a pre-op teaching program, either face-to-face or by module, in terms of pain control measures post-op surgery. So you've got those, the pre-op teaching is what you're going to manipulate. And the control is also a feature of experimental design because increased control results in a decrease in bias or untruths or inaccuracy. See, the researcher has the power to direct or manipulate the factors to achieve a desired outcome. For example, that pre-op teaching goes to an experimental group where the control group gets the usual or routine education. So the researcher will control the duration, the timing, the content, and the teacher of each of these sessions. So you see how this plays out? I'm so excited. It's cool. All right, other characteristics of a true experiment includes randomization. Well, and what this basically means is that every subject has an equal chance of being included in the experiment or the control group. Now think about that. Every subject has an equal chance of selection into the experimental group or control group. Now what this does then, as you are randomly putting your subjects into these groups, the researcher's not controlling, so that you have a truer flavor or a richness of the data about, because you're not doing any pre-selection or bias. You see? You've got this random sample. This increases the rigor and the generalizability of those study results. So just know that. Now here comes lots of fun, and I don't want you to have to commit these to memory. Just kind of understand the concept, because page 153 of your text really begins the formula for quantitative research designs. And I want you to understand that the R will equal that randomization we just talked about. That those random subjects are placed in a group. I'll tell you more later how that happens. But the X is a representative of the intervention. It's what the cause is. The O is the observation or the measurement of the effect or the dependent variable. So when you have a post-test only design, each subject, remember, has an equal chance of being assigned. Well, what happens here is you have that randomization. You have two different groups. You have the experimental group, which is the RXO. They're randomly assigned. They have the intervention, and then you measure the outcome. The second group is randomly assigned, has the usual or whatever normally happens intervention, and then you measure the outcomes. And then you compare the data from those two groups. See? That's the post-test only design. This isn't so bad, is it? Okay, now we move to a pre-test, post-test design. And it's very similar to what we talked about, that, again, the groups are randomized and both are given a pre-test. You see those O's there. Okay, so they're in the experimental group and the control group, but they both get a pre-test. And then the experimental group gets the intervention, and then you measure the outcome. Because what you're able to do then is compare the two groups prior to the intervention and after the intervention. You talk about some wonderful, rich data. Wow. So the experimental group receives the treatment, which is the independent variable, and the control group gets the normal or no intervention, and then both are reevaluated, and then you compare. I'll give you an example. There was a group, Simpson and James, around 2005, that looked and studied immediate versus delayed pushing in women who were in second stage of labor to determine the effect on the fetal well-being. Now, women were randomized via computer, and all of their names went into a program, and they were given a number, and then they were selected into the groups. So then they had some special procedures They gave them all a pretest. Some of them had some special procedures regarding pushing, and then they evaluated the two groups. So you see, pretest, post-test, experimental design, quantitative research. You gotta love it. Alrighty, we're not done yet. Here's yet another crossover design, and you're going to see this a lot in the literature. Because what you're looking for in analysis here is a comparison of pre-test and post-test scores, and a comparison of the control and the experimental groups, comparison of pre-test, post-test between different samples. And the beauty about this design is that in this design there's some sense that the subjects are serving as their own control group. So you're getting a mix of data. And so remember that really this is the design where the subjects kind of serve as their own control group. Highlight that. The subjects are assigned in two random groups. They both receive a pretest. Then they choose one or two of the interventions, the independent variables, that's that XA, XB. Then there's another post-test. And then they choose the other independent variable. And then there's another post-test. So you see those multiple levels because you can compare that first pretest, the intervention, then the outcomes. Then you measure those two differences, and then the other intervention, and so you've got multiple ways to compare that data. Let's say the study I'm thinking about has to do with colostomy bags. There were some different types they were using, two different types. This was in a study, I think Vorgel, where all subjects, it was randomized with patients who had colostomies, and they were given a pretest about colostomy care and use and leakage, etc., etc. Then they were able to choose one of the two bags being studied, and then they measured the data and gave them another post-test. What did they think about the bags that they used? You know, how much leakage, how much irritation, yada yada. So then they let them choose the other bag for a period of time, and then they went back and did a post-test analysis on that. So then all subjects got exposed to both of the independent variables, but in different order. See, isn't this cool? Okay, this is the last one I'm going to burden you with, but you're going to see this also. This is the Solomon 4 group design. And it's really the main thing to understand here is that this design allows the researcher to evaluate the interaction effects between the independent variable. And you consider, this is considered the most prestigious experimental design because it minimizes threats to the internal and external validity. So you might want to hang on to that fact. And it's very similar to the crossover design, but there again, there's just a little more rigor to it. So, not that I want you to commit these to memory and detail, but just understanding that these are the formulas for the quantitative design that you're going to encounter as you conduct research. All right, control group conditions. These are very important because you've got your experimental group where you're manipulating the variable or the intervention, but your control group needs to be pretty solid too so that you don't have skewed or inaccurate data. And page 155 really tells you what conditions need to exist because your control group needs to be pure with the usual or normal standard of care that is used. Now, you'll see the last, sometimes they'll use placebo or no, something with no therapeutic value, and that happens. And sometimes this is the area you have to really use caution in terms of the ethical principles that we have already covered. because you see that one about the lower dose or intensity of treatment, or only portions of it are administered. And delayed times or treatment or intervention are considered okay. But things like if you were doing clinical trials for a chemotherapy agent, and we all know chemotherapy is administered based on cellular replication, so delayed treatment could have a negative impact, and ethically those are things you have to account for and control for in your control group, because you don't want them to suffer because of that. So, but know that these are okay in terms of it might be an educational encounter or a treatment modality. But control group conditions are important. Now, quasi-experiments. This is a quantitative research design, but it is different than that experimental design that we just discussed, because they lack randomization, or they lack a control group. Those are the two major things. You may find your quasi-experimental research comes from a convenience sample. Generally, the researcher is using an existing group, and I'll give you an example of my dissertation was quasi-experimental, and that I used one group of students, but I used multiple post-tests after every intervention. And this was a naturally occurring group. And the beauty of that is that sometimes these naturally occurring groups or convenience sample really holds more real-world application of findings. But you're going to see quasi-experimental a lot because of the sampling. But remember, they lack randomization and or a control group. Now, yay! Here we go. Within subjects quasi-experimental. I want you to know and appreciate the basics here. Quasi-experimental are easier to conduct and often more practical. But then that makes it more difficult to infer cause and effect relationships from the finding. But you see they've got the same, you don't have that R up there because there is no randomization. But you've got the intervention, you've got yes, the pre-test, and then you've got the intervention, and then you have the post-test. And that's with one group. And the time series design, that is what I used with my dissertation. You've got the test, intervention, and then the follow-up test. So just kind of understand the principles of that, and that there's no randomization and there's no control group. You're looking at one group. Okay, excuse me, more fun. Non-experimental studies are quantitative. It is quantitative, and it is different from qualitative research. So know that. And that basically all non-experimental research is descriptive, because there's really nothing being manipulated or controlled. Yet it is quantitative. We're still having rigor and numbers and looking at relationships. And you're not all the independent variables of interest can be manipulated. For example, if we're going to do research on smoking here, well, you can't make your subject smoke or not smoke. That is unethical. So just remember, there's really zero cause and effect here. You're just looking at relationships. And you're going to see this in the medical literature as observational. And a lot of nursing research is and has been non-experimental. And this type of research is powerful because, you know, it really helps you deal with the ethics thing. Because humanity, as we know, we don't really need to tolerate inhumanity, for sure. Okay, so we have types. Aren't you happy to know that? Types of non-experimental studies. Yes, they're correlational designs. These really examine the strengths of relationship between variables, either positively or negatively, in a single group. Now remember, correlation does not really prove causation. but it's just association. And these studies are really, certainly they are weaker than randomized controlled trials. Why? Well, you're right. If you said because there's no randomization and there's no control of the variables. That's right. That's why they are weaker. But they are still powerful. And you're just looking at association of variables. Now, there's two types of non-experimental studies of correlational design. Woohoo! There are two major types, prospective and retrospective. Let's talk about prospective for a minute. This is also known as the cohort design. This prospective correlational design links the present to the future. Lots of studies out there now about childhood obesity and the onset of type 2 diabetes. That is, you're not going to have a randomization of subjects, but you're going to have, lots of opportunity to link what's happening now with the potential in the future. Or even increase cholesterol levels and the incidence of coronary artery disease. That's another example of a prospective, non-experimental, quantitative research. Retrospective designs, also known as case control, link the present to the past, also called ex post facto studies. Love all this terminology, don't you? But basically, an example would be looking at fear responses of children during physical exams. Well, the researcher here may go through lots of historical data like the chart, looking at previous unpleasant experiences like injections, venipuncture, pain, whatever associations, throat swabs, and then measure current fear behaviors like increased pulse rate, anxiety, trembling, crying, those kinds of things, to make that association. So that would be an example of a retrospective design. All right. Y'all are doing great because we're moving now to descriptive research. And this is the second really broad class of quantitative and non-experimental studies. Because not all research is cause probing, but we are looking to describe. And this type really describes the relationships between variables, but it is stopping short of inferring cause and effect. It may just say these things happen together, or when one happens, the other happens. So, just know that descriptive research is powerful, and it is quantitative. All right, page 162 of your text looks at timing and research design, and includes the when and the how data are collected. It's kind of like planning a wedding. There are stages to it, time frames, deadlines, and the same is true of your research design. Your cross-sectional design will be happening usually at a single point in time, but it can occur at multiple times over set intervals. For example, my dissertation, I collected data in a cross-sectional design 3 times over 6 months. There you go. Longitudinal designs are collected 2 or more times over an extended period. And this may be over months or years. And the Jackson Heart Study that is looking at African American cardiovascular health is years. And it's yielding some very powerful information. Now, the challenge to these longitudinal studies, though, is the attrition rate. And that's when you lose your subjects. Subjects die, especially in the cardiovascular study. They die, so you lose that. Well, the data is important about the death, but certainly over the long haul. And that's just when the participants or the subjects drop out. And so it is more of a problem So you just kind of have to account for that in your sample size. Now, be sure to read page 164 because it really highlights your techniques of research control, which are important. I'm not going to go into them in detail here, but just know about them because you want to make sure the results are as pure as possible. And these techniques that are listed there are really for controlling variables and are built in, like insurance. You build them in so that your findings are pure. And so here's some characteristics of building in. So how do you know the results are pure or sound? Well, you look at the research design and validity because you have statistical conclusion validity. And numbers don't lie. You know, do the numbers make sense? Are they showing a relationship that is true? Now, of these types of validity, we're going to talk more about them, but the construct validity is probably the most difficult to measure because you're really looking at how well or accurate did the instrument, the questionnaire, the tool, the survey, the whatever you used, measure the construct, that really abstract thing like caring, healing, whatever. How well did it measure that? And that is probably the hardest of these four to account for. So, here's some threats to statistical conclusion validity that you just need to be aware of. If your sample is just too small, well, numbers don't really lie unless your sample size is below 100. And maybe there's some sampling or bias errors. Maybe the randomization didn't occur as it should have, or it's really not random when the researcher says it is. So that would be a statistical conclusion validity threat. So also there's a weaker cause here. You know, the intervention therapy session had different people conducting each session. Well, that individual effect that person brought may actually alter the results because some people may do things differently or have some kind of a different control or relationship with the group. So your individual effect may alter the results. So you are really looking for these things in your research studies. Threats to internal validity. Well, certainly the selection threat, that bias that arises from pre-existing differences between the groups being compared. Quasi-experimental and non-experimental correlational study designs are more susceptible to this threat to internal validity. And these are really the main threats listed here. That selection threat, the maturation threat, just because the passage of time, comparing apples to oranges, like I mentioned with those between the groups being compared, they're apples and oranges, so it doesn't make sense. So that's an internal validity threat. Timed out, it's just there's a maturation threat. Like there was a study that I have done years ago about online education in 2003. Well, my word, today, it's totally obsolete. Any of that information, and if I was going to replicate, I'd have to start from scratch. Also, the mortality or attrition threat, and certainly, again, your subjects die, or in the instance of, let's say, an adolescent drug use study, your subjects age out. They get too old. So those are internal validity threats. And here's external validity threats. Isn't this fun? Yes. Let's say the external validity has to do with just inadequate sampling. Because then if you don't adequately get a representativeness, you are not able to take the study findings and apply them to different groups or populations. An example of that has to do with breast cancer, perhaps. In America is different than Asia and Germany and Europe and those places. And the enhancing internal validity can sometimes have adverse effects on external validity. And the reason for that is because it just you make it so narrow and specific that you limit the generalizability. And the other threat to the external validity has to do with the Hawthorne effect. And this is very difficult just to measure sometimes. And it is when your subjects in the study behave or respond differently just due to the fact they are being observed. It's kind of like you coming to a complete stop at the stop sign when there is a policeman there, as opposed to doing a California slide through the stop sign. You know, you behave differently when you know you're being watched. And the Hawthorne effect will happen in studies. You know, when you're asking people to respond to a questionnaire or a behavior or whatever, and that is a threat to the external validity. So, know those things. As we breeze into Chapter 10, Basic Sampling Concepts. So, gosh, we have talked about the major types of quantitative research design, and you know a ton. So now we're going to talk about quantitative sampling plans. Wow. For example, the population is the aggregate of cases in which, you know, the researcher really is interested in. Like example, all RN to BSNs in the United States. That's going to be our population. Well, our sampling will be a selection of that population. And it's going to be all RN to BSN students at the UMC School of Nursing. Isn't that cool? And the samples are just a part of every research design. It's the who, the what, and the when, and the where. How they're selected, where they are, those kinds of things. Now, eligibility criteria is important to discuss. You're going to look for it in your research. What is the inclusion criteria? What does it take to be in the study, to be a subject? Well, it would be full-time status, fully admitted, second semester, RN to BSNs. Then there's exclusion criteria. Well, what rules you out? Well, if you're a part-time student, if you are less than 30 years old or greater than 5 years of practice, that may be exclusion. That means you can't be in the sample. So here's some concepts just to understand, kind of get a part of your DNA here. There are strata, subpopulations of a population. For example, there are the fabulous UMMC RN to BSN students. There are those of you who are different in age, clinical specialty, gender, brown eyes, blue eyes, etc. So that's the strata of our population. There are subpopulations. Then you have the target population, which is the entire population of interest, which is also all RN to BSNs in the United States. Then your accessible population, again, is going to be that portion of the target population, which is all RN to BSN students at UMMC. So you see there's some overlap in these terminologies, but they all kind of mesh together. And the bottom line is the sample is who actually participates in the study. And it may only be a few of the RN to BSN students at UMMC School of Nursing willing to participate. See? That's the sample. So there are two types of sampling. Remember, the better the sample, the purer the results. Now we're moving into the stats, so y'all hang tight, kind of. Non-probability sampling just says that there's really no selection of elements. There's no random selection. It's you use what you have available. Kind of an all-volunteer. There's no random sample. Probability sampling does involve random selection of elements. each element has an equal independent chance of being selected. Now, what type of research is this with? You're right. Experimental, true experimental research. Very good. Non-probability sampling would be with quasi-experimental and descriptive. See how much you have learned? This is exciting. Just remember that random sampling is a systematic selection process. So first of all, let's talk about non-probability sampling in quantitative research. There again, this is going to be in your quasi-experimental and descriptive types of studies. And you need to know these. There's convenience sampling. These are on page 178. You use what you have. That you use who you have before you. And of course, this type of sampling does increase sample bias and limits generalizability. Because if I look at all UMMC RN to BSNs as intellectually superior to other RN to BSNs in Alabama, the region, the nation, I know that's true, but that's going to increase the bias. And of course, nurses use these a lot, convenience sampling, just because it's just easier to use sometimes. There's quota sampling, and this is just breaking it down into small groups so that you get a certain number. Like I might need 50% male ex-smokers of greater than 10 years, and I need 50% females of ex-smokers of greater than 10 years. Then you've got consecutive sampling. And this is where you're building the samples as they come. Let's say you have a COPD clinic and you are doing a smoking cessation program. Well, you've got the COPD patients there, but they can give you the names of other smokers in their household, so you're building your sample as it goes. And that's kind of like hand-picking subjects, that purposive sampling. Hand-picking subjects, believing that the subjects are typical or representative of your target population. For example, if you wanted to research problems with portacaths post-chemotherapy, well, your purposive sampling will be maybe from an oncology clinic where the researcher personally knows several clients with issues. Of course, there's a bias problem in there with the sample, but it's also great data. That doesn't mean you can't use it. So, that has to do with non-probability sampling. Let's move on to probability sampling. This provides the most rigor for quantitative studies. You're going to see this in true experimental research. Increased rigor equals pure results and truth. Remember, each subject has equal chance of selection and the independent chance of selection into the experimental or control group. Woo! We're going to talk about each one of these. This is some riveting stuff. When you think of probability sampling, usually there are numbers tables that are associated, where instead of you assign subjects a number on this, it could be thousands of numbers. And then you as a researcher may decide to select every third number on the table for the control group and every fourth number on the table for the experimental group. So you see, if you had thousands of numbers and you have subjects assigned to those numbers so that nobody knows who the subject is or anything about them, it's just by number, and so they have a random chance of selection. All right, this is exciting. Simplified random, stratified random, and systematic sampling. Woohoo! All right, simple random sampling. Once you have identified the accessible population, you number them. This is what I was talking about, the sampling frame. It's really a list of all the population elements. And you can use computer generated nowadays. This is great. You can use like the bingo balls or slips of paper in a hat and pull out however many you need. Isn't that cool? Till you get to your desired sample size. And simple random sampling, and you need to hang on to this, is the most unbiased probability method. It's going to give you more pure data. So just kind of remember, it's numbers tables. You have a system selection, 2 down or 2 left, and select 15 or 100, however many you need. But it's totally objective. I like this. Simple random sample. Stratified random sample. Well, this is used because you want to attempt to enhance representativeness. The population is divided into the strata. You remember we talked about that. Age could be your clinical specialty. RNs with brown eyes, RNs with blue eyes. And you will then determine the number for each group. You may want 100 in each of your strata. And then you do the simple random sample approach like we just discussed. Isn't that cool? So it enhances representativeness. Cluster sampling is yet another. And this really groups rather than individual people are selected from the population. For example, we might look at all RN to BSNs from UMMC, but also from USM, Alcorn, UAB. And you're going to see these used in national surveys for sure. But you start larger and then you move smaller, states, zip codes, households, or you can do schools of nursing. And then you do the random sample from the clusters. Now, you get tons and tons of data. And the thing to really just know is these stats used in cluster sampling are just very complicated. But you can also get powerful data out of using the clusters. And you're just using groups rather than individuals. Let's talk about sample size, because that's always what people want to know. Are there enough subjects in this study to make it true, to make sense of it? And this is just those who actually participate in the study, the final sample. Usually, the greater the sample number, the better the representation of the population. Now, for descriptive, non-experimental, quantitative research, a sample less than 30 or greater than 500 can be justified. A sample size of 100 really ensures the benefits of what's known as the central limit theorem. And this just says that the sample value is distributed around the norm of the population. More on that later. So you really want to know, how many do you need in a subject pool to adequately test your hypothesis? And this is where the power analysis comes in. It's the absolute minimum needed to be declared, and you declare that at the beginning of the study before data collection begins. So sample size is important. Data collection in quantitative research is really in two domains, new data and existing data. But here's what I want you to hang on to about data collection, because what it is the measurement of data. And it is the measurement of data. It is the process of assigning numbers to variables. Let me say that again. The measurement of data is the process of assigning numbers to variables. And it can be done by counting, ranking, comparing. For example, blood pressure, anxiety, heart rate, all kinds of things. We're going to talk more in detail about that. But just also remember that the data collection method, also known as the research instrument or tool, are declared and set in stone at the beginning of the study, before you even begin collecting. Major types of data collection methods. Oh, this is some good stuff, and you've probably participated with some of these data collection methods. The ways it's collected. Self-reports. This has to do with, it can be verbal, can be interviews, questionnaires, which is the most common. Know that. Psychological tests, attitude scales. Those are going to be the self-report collection methods. Observation can be behaviors or characteristics. Biophysiological measures are going to have to do with just that. Arterial blood gases, blood pressure, pulse, all concrete numbers, urine output, laboratory findings. So let's go back to those self-reports for just a minute. Because there are structured self-reports, and quantitative research uses these extensively. And the more structured, certainly the more accurate the data. And remember, the target data is determined in advance of the data collection, so you're not really exploring issues with these. There's a formal instrument. Can be interview or can be questionnaire, and again, questionnaire is the most common. And it's really for a good reason. Usually the questionnaires are pen and paper, but certainly now electronically is the way to go. I've used both of these myself. Love the electronic version because it's just more efficient. So let's talk about advantages to questionnaires when you're collecting quantitative data. Lower cost, and there's greater anonymity and privacy because you do not have subjects disclose who they are. There's that lack of interviewer bias too. On a questionnaire, you're not going to have the influence of an interviewer looking you in the face. They are very quick, efficient means of obtaining data from a large number of respondents. And they are easily testable for reliability and validity. Now, some of the disadvantage of a questionnaire may, again, if you have to mail them or buy a computer software program, etc., it may be costly. Also, a disadvantage is sometimes you have a lower response rate. You may send it to 500 people, but you may only get a 20% response rate, which, will affect your results. And then you may send out this questionnaire, and they may not answer all of the items. It may be 20 questions, and they only answer 10. Well, what do you do then with those 10 questions that weren't answered? The other disadvantage is it doesn't allow the subject's opportunity to clarify, like, what does this mean? What are you thinking? And there is sample bias. Why? Think about it for a minute. You're right, because your respondent must be literate, be able to read in order to answer the questionnaire. So therefore, you've automatically got built-in sample bias by using a questionnaire. And they really recommend there's this FLESH reading scale, or the FOG scale, that all questionnaires aim for a 6th to 7th grade reading level. But there again, if you're illiterate, you won't be able to do the questionnaire. They also recommend, they being those who know all, the researchers, the questionnaire language should be simple, clear, and specific. No slang, no medical jargon. Questions less than 20 words, and it should take less than 10 minutes to complete, or you will lose your audience. So, that's that about questionnaires. Interviews, that face-to-face or phone thing. Usually you get higher response rates. You can get more diverse subjects. You give the opportunity to ask questions or get additional data that maybe you weren't aware of. So you have a high rate of response as an advantage from a wide range of subjects. And you can also look at verbal and nonverbal cues, with most of the data being very usable. Now here's some disadvantages of the interview. The training of the interviewer, number one, it's time consuming and expensive, and you have to make sure everybody's kind of singing from the same songbook. Your subjects may be anxious or influenced by that interviewer. Remember the Hawthorne effect? Let's say you are doing interviews for, young women, interviewing young women on post-abortion grief. One of your interviewers is a grandmotherly type. Do you think you're going to get truthful responses? Maybe, maybe not. Could be an influence. So that might be a disadvantage. Here are some other types of data collection methods, or some psychosocial scales. And page 187, table 10.3, gives you great examples of a Likert scale. You're going to see that an awful lot, because these scales assign a number score along a continuum. And so that makes it very easy to compute. And so the Likert scale is going to be the thing you see one of the most of. And this is a form of that self-report. And it's really a more precise means of measuring phenomena. And you know, one that you use regularly may be a pain rating scale. That's used quite a bit. So, know about the scales, especially the Likert scale. And the Likert is really, there again, one of the most common, and it uses declarative statements like, I read the required text assignments always, sometimes, never, like that. And it's at the ordinal level of measurement. The somatic differential scale kind of rate a position or an attitude along a continuum. For example, RN to BSN respondents were asked to rate nursing research using 4-word pairs: meaningful to meaningless, valuable to worthless, stimulating to boring. So that would be an example of a somatic differential scale, so that you rate somewhere in that continuum that thought. So these are some more self-reports. And the fourth type of scale used is a visual analog scale, and we use these daily in practice with the pain. They are being used with increased frequency in nursing research because it really measures, and this is what I want you to hang on to, know this. These measure the strength, intensity, and magnitude of the variable or the characteristic. This is what the subject experiences. Fatigue, dyspnea. It's a great tool. And it's really, there are several out there that already have wonderful validity and reliability established. So, know the visual analog scale. All right, now when we get to structured observations, that is yet another form of data collection. In your book, there's a brief section on cue sorts and vignettes as other self-report data collection methods. They're really not seen as often in research, but you may see them. Just read over them. Because really when we get to observational methods, that is a data collection method in non-experimental quantitative research. And the data is just collected through visual observations. And it can be structured and unstructured. Don't you like that? So this is strictly observation. It is non-experimental and it is quantitative. And it's the unstructured observation is in qualitative research like watching a lab rat, so to speak. You know, the researcher observes, the participants perform in a specific setting. Where your structured observation, the quantitative researcher is going to define what and how the observations are made, recorded, and coded. Let me give you an example. There was Lau, Yang, and Cho, a study that determined the effects of developing supportive care educational programs for nurses on their caregiving behaviors to preterm infants. And so what these researchers did was they were watching and recording nurses and infants' behaviors during bath time. So that's an example of a quantitative observation data collection method. Did you like that? All right, observational sampling. Time sampling is important because there are just going to be intervals for this observation. I don't think you can do it 24/7. It'd be difficult. But time sampling is usually a single event or behaviors, like how many times the nurses touch a client with HIV, or how many times a nurse speaks to a hospice patient. That's going to be just a sample of time intervals. And then there's going to be the event sampling. And this involves the observation of the entire event. That's like the preterm bath that we just talked about. That researcher is looking at that whole event from the time the nurse picks up that preterm infant to the time the nurse puts that preterm infant back into the bassinet. Isn't that cool? So those are just some differences when you're looking at collecting data through observation. You're going to be looking for how many times something happens versus what happens during an event of time. I love it. Okay, biophysiological measures in vivo. Well, in vivo has to do with things that occur within the organism, like blood pressure, temperature, arterial pressure, those kinds of things. In vitro would be those things outside, like a urinalysis or arterial blood gases. And you're going to see these collected a lot in quantitative research and compared to other variables. So just know that that is yet another very profound data collection method that we use in nursing. All right, moving on to Chapter 11. This is fun with measurement and data quality, also known as statistical analysis. Now, I don't want you to get bogged down in the dynamics. I really kind of want you to understand just the overview, because it is important for you to understand how the numbers report and are they pure and true. Because this is really a pure feature of quantitative studies. So will you find statistical analysis in qualitative studies? Not really. It is purely quantitative. And remember, measurement is the process of assigning numbers to variables or data. So it is a language of communication. If the patient's temperature is high, that's not telling you much. What you want to know is that, people receiving bone marrow transplants will end up with temperatures of 103, so many hours into it. It's the language of communication, this measurement. All right. Know the next 3 slides. This is a brief overview too. It's a mini stats class review because you've already had this. Remember, there are 4 levels of measurement. There's the nominal. That's the lowest level of measurement, and it has to do with things like gender, marital status. It's just classifying. Then there's ordinal. This is a ranking based on the attribute. It might be anxiety level, being mild, moderate, severe, or a category. Then there's interval, where there's going to be a scale, like thermometers or weight will be on interval. Then ratio is going to be a scale, but it's got total absence as part of that, a meaningful zero, like my bank account. There you go. So, know about or recall about these 4 levels of measurement. And remember that there are 3 measures of central tendency: the mean, the median, and the mode. Now, why is that important for statistics? Well, because with all of this data that we're collecting and assigning numbers to data, there's the opportunity for errors of measurement. And that is, the measurement error is the difference between the true measure and what is actually measured. Now, unfortunately, measurement errors in research can be random or they can be systematic. They can occur just once or they can be throughout the whole study, which really messes up your outcome. So these, when you look at errors of measurement, just know that it is the obtained score, but it is the true score plus or minus the error. Like we may be measuring anxiety on airplane flights, and we have a 2+ anxiety on our visual analog scale, but the true score is 0 anxiety. And then so the error was going to be +2, that we've got somebody who's hysterical and can't get on the plane. So you see how it can skew the data. There again, it can be random or systematic and can trash the results. And the other thing is to remember, all instruments and data collection methods really have some degree of error in them, but you really want it to be as reliable as possible. And that reliability is so powerful because you're looking for truth. Does this instrument really consistently and accurately measure what it's supposed to? Like the Center for Epidemiology Depression Scale. If you repeatedly use it with a subject in a short period of time, you're expecting that the scores should be similar. Meaning that, if I gave you an anxiety scale every time we gave a test, I would assume that those findings were going to be similar every time we gave you that scale, because that's going to indicate some degree of reliability. Now, the reliability coefficient is just a number that determines how efficient or how small a difference there may be in terms of error measurement. Coefficients, and this is what I want you to hang on to, below 0.70 are not satisfactory. That means that that tool, that instrument, ain't so good at measuring what it's supposed to. It has poor reliability. Whereas, if it's 0.80 or higher, that means there's stability of the instruments. There is a consistency with repeated measures. We're going to talk more about this, but it is designated with a lowercase r, meaning reliability. And you'll be looking for those in your research reports. One of the things you want to do is control for measurement errors. It's important because you want truth, purity of your results. And there's 3 aspects of reliability that you try to evaluate: stability, internal consistency, and equivalence. Now, stability of your tool is the extent the scores are similar on 2 separate administrations of an instrument, a test and a retest. My dissertation, I'd use the same tool over 3 times in a quasi-experimental design. But after each tool was administered, there were variables and interventions that happened that changed the scores. So while my tool remained, it had high reliability scores, so I could know that the results were true. I hope that makes sense. as we talk about internal consistency. Now this is determined really after one administration of the instrument. And here the Cronbach's alpha is king, because what the internal consistency measures is the extent to which all items on the instrument consistently measure the construct. And this is the most widely used approach to assessing reliability. But if you have a 30-item questionnaire, then each of those 30 items is evaluated using the Cronbach's alpha. So you're looking for coefficients with the Cronbach's alpha from, if it's a 1, that indicates perfect reliability. A 1.00 indicates perfect reliability. A 0.00 means a no reliability. So these are important and to determine for each of the items on a questionnaire. Equivalence. Really, this is the degree to which two forms of an instrument obtain the same results, or two or more observers obtain the same results when using a single instrument. For example, you have a study of two falls risk assessment tools with elderly hip fracture population. Well, the correlation coefficient was 0.96 and 0.83 respectively for those two tools, while the inter-rater reliability of those using the tools was high. They determined that both tools over-predicted the risk of patient falls. So you see, you're looking for relevance of structured observations and equivalence. Does one measure, or do tools measure what they're supposed to? Now, the second very important criteria evaluation for a quantitative instrument is validity. And does the instrument measure what it's supposed to? Validity, like reliability, is really not an all or nothing phenomena. It is measured on a continuum. And remember, there are no perfect instruments, and validity will vary from sample to sample and situation to situation. For example, if I administer a depression scale in a mental health clinic, that is going to be different in terms of validity if I administer it in a cancer clinic. You see? So, there are 4 aspects of validity, which we're going to talk about. I want you to know them. And validity testing really evaluates the use of an instrument for a specific group or purpose. Does it gather the data that it is intended to gather? Face validity is really a cursory exam that shows that this tool is measuring what it's supposed to measure. And what you're going to find is that experts examine this content for face validity. And you do not use this type of validity alone because of its subjectivity. So you use it in terms with some other types of validity checks. For example, you're going to see sometimes where face validity of this tool was obtained by using 3 master's prepared mental health nurses. That is how face validity is determined. Content validity is really concerned with the scope or the range of items used to measure a variable. Are the number and the type of item adequate to measure the concept or the construct? Is the content solid? Does it actually measure? The actual degree of content validity is really never truly established. It is only estimated. So when you see content validity, this content validity index, you're going to be looking for a 0.90 is the standard for establishing a scale's content validity. And again, it is for each item. So a 0.90 or greater indicates that question or scale is adequate and valid to measure the concept or the construct. content validity. Criterion-related validity. Woohoo! This assesses the ability of an instrument to determine the subject's responses at present time or to predict subject's responses in the future. Don't you like that? It's a crystal ball kind of thing. For example, let's say we have a tool that measures irrational beliefs. And this is the attitude and belief scale. Irrational attitude and belief scale. And the researcher believes that these irrational beliefs are also indicative of other signs of psychological disturbances. So, using concurrent validity is examined by looking at the scores of 42 people. And 42 people take this irrational attitude and belief scale, and then they take other 4 other measures of anxiety, depression, yada yada. And so then you do a comparison there, and you're saying then that yes, the irrational attitude and belief scores were high for people who also scored high on the 4 other subscales of psychological disturbances. So that gives you concurrent validity, which is a part of the criterion. So what you're wanting to say is that, all of these things meld together with what's out there in the literature and what is used, and that it is valid. So, but here's the one I want you to really, really know. Construct validity. This is the key criteria for assessing the quality of a study, and this is the one that is most often linked to measurement error. Know that. Most often linked to measurement error. Does the instrument measure the construct it is supposed to measure? Like that irrational attitude and belief score. Did it really measure that? Is it derived from an underlying theory? Is there a theoretical basis? And there are really 2 methods to assess construct validity. There's a group technique, known group technique, and a factor analysis that your book really talks about. I'm not going to go into detail because I don't want to put you in a coma. But just know that really all of these are a part of how we evaluate and critique our data collection or instrument methods to see that they're worthy and that they're going to get to the core of our data and give us something that's reliable. Did the research report what the instrument was, what the validity was, what the reliability was, and is it measuring the appropriate levels of measurement? So there you go. That's what I want you to know. Okay, now this is going to be a brief review because this is getting us to the statistical analysis. And you've already had that course. So let's talk about descriptive versus inferential statistics. For quantitative studies, descriptive statistics organize and summarize numerical data and examine the characteristics of a sample. Now, inferential statistics make inferences about the population. It's concerned with the bigger piece of the pie. And you will make judgment and assumptions based on these inferential statistics, but there's a chance of error because it's not as detailed. So remember, descriptive stats look at a sample, and inferential stats look at a population. Isn't this fun? Frequency distributions, you're going to see these a lot because they really help to impose order, and it is the simplest way to present data. It's a visual picture. Just simply, how often does it happen? And it's really appropriate for all levels of data, nominal, ordinal, interval, and ratio. And values are listed highest to lowest, so it's really easy to see. And we're going to talk more about frequency distributions. Because when we look at the shape of our distributions, we're looking for symmetry. They are either symmetrical or non-symmetrical. When we look at symmetrical distributions, this is the normal bell curve, which I'll show you in a minute, but this is where both halves are really the same at equal intervals. But however, we see skewed shapes frequently. Non-symmetrical are called skewed. It is off-center. It has a hump. If the long tail points to the right, that means the hump is to the left. It's a positive skew. And vice versa. If it is the long tail to the left, the hump is to the right, and that's a negative skew. Let's look at these. Here we go. A positive skew is an example of a variable. Let's look at income here with number A. You can see that when the hump goes up, a lot more people have small or middle incomes. And then when that little tail comes down, that equals the very, very rich. There are fewer of them. Okay, if you look over here at B, you can see, let's look at age of people with chronic illness. Well, this is young people here at this corner of B. Very few people, young people, have chronic illness, and you see the hump grows as people get older, and by George, that's where most of the population resides. Now, here's some symmetric distributions. Number A is symmetrical unimodal, one peak. B is bimodal. And these just have to do with our measures of central tendency that help us describe the average, typical, most common value of a group of data. And you might see them represented in those bimodal and unimodal types of graphs. Central tendency, the mode, it just most frequently occurs. If I look at all of your RN to BSN IQ tests, y'all are all at 130 and genius. That is the mode. The median divides the scores in half. And let's say all RN to BSN's IQ is between 110 and 150, with half of that being about 120, and it's equal on each side. And the mean is just the average. The average RN to BSN IQ score is a mean of 125. You add all of them together and you divide by the number of subjects to get the mean. There you go. Variability, also known as variance. And it is an inferential measurement. And it is step 6 of a calculation of the standard deviation. You don't have to do this, thank goodness. But in other words, it is the standard deviation squared, and how we come up with variance or variability. And what it basically does is tells you how far a group of data is from the mean or from the average. For example, my research and teaching methods in Generation Y was very homogeneous. There was very little variability because everybody was the same age, essentially. And so all the groups, all the questions were very similar with very little variance. Indexes of variability. There's range, and this is the highest value minus the lowest. Simplest measure of variability. RN to BSN IQ range is 120 to 160, genius level. Now, standard deviation, you need to put a star by this, is the most widely used, and it describes how the values or the scores vary around the mean. Tells you just how spread out the scores are in a distribution. And here is the normal bell curve. You're going to find this in page 220 in your text. And you can see that there are equal standard deviations from the mean in the normal bell curve. If you look at one range, that 14% at the -3 standard deviations to the 14% at the +3 standard deviations, all of these scores are 6 standard deviations apart. Range is from 20 to 80. So the standard deviation, again, takes into account all values in a set of data. And remember, it just helps you look at the variance from the mean or from the average. How far do those scores go? Now, bivariate descriptive statistics really look at two variates. And these descriptive stats look at relationships between two variables. And you're going to see these in contingency tables, those crosstabs where they display relationships between sets of nominal and ordinal data visually. Great example on page 221, table 12.4, looking at variables of gender and smoking. I encourage you to look at that. And then there's those correlation coefficients. We've really already talked about that to a degree, because remember that small r we looked at? There are some specific procedures that you're going to be looking at the relationship between these two variables using correlation coefficients. Remember, correlation does not equal cause. Correlation coefficient is a statistic that presents intensity, magnitude, and direction of a relationship. The most widely used is the Pearson's R, being that little r that we talked about earlier. And a negative relationship you're going to see is at a 0.00 to a -1. And I'll give you an example in my dissertation where I looked at self-directed learning concepts of students who were experiencing problem-based learning, which is a teaching method. Unfortunately, what I discovered was the more the student experienced that problem-based learning that forced them to create and be responsible 100% for their own learning, the greater their confidence, or their level of confidence in their ability to self-direct their learning occurred. So they lost confidence in their ability. And so that was a negative relationship. A positive relationship might be increasing anxiety levels or pulse rates with airline flights. That's going to be a positive correlation, you see. So if you have a small r, being the Pearson's R, a positive 0.80 indicates that the value of one variable increases the value of the other variable. That when these variables occur, they both go up together. If you go have an airline flight, you've got anxiety going up. Or if you have anxiety, you have pulse rates going up. That's a positive increase. And that's really what the correlation coefficients do. If one variable increases, the other one decreases, that's negative. Both go up, it's positive. Alrighty, isn't this great? I love it. Y'all are doing great. We're getting close to being done. And describing risk. Well, because with all of this, you've got these tools, you've got this validity, reliability, we've got the statistical analysis. Well, because you have to look at the risk in here. The big emphasis on evidence-based practice really has to do with reading and critiquing multiple research studies and looking at contingency tables and making clinical judgments that affect patients' lives. So you want to make sure that what you're looking at is solid. And so you do that by understanding risk and absolute risk. And that's how you determine whether to implement something into practice or not. Now, inferential statistics is the second broad purpose or type of statistics used. And remember, it looks at population, not sample or individual. And this really gets into the nailing jello to a tree kind of thing, but hang in there, guys. We are getting close to the end here, based on the laws of probability. And remember, when you're looking at inferential statistics, the sample is chosen as a representative of the population. And so this theoretical distribution is really a phenomenon in which the sample value tends to be normally distributed around the population value. And that again is known as the central limit theorem. So we know that UMMC RN to BSNs have genius IQ scores. And while those are clustered around the population means of all RN to BSNs in the nation. But we are at the high end, of course. So, sampling distribution of the mean. This is again a theoretical frequency distribution. And it's based on an infinite number of samples. So really, that's really all you need to know. It's a theoretical frequency distribution. You know, we study the UMMC RN to BSNs, but we know that U are superior to all the other RN to BSNs in the nation. So when you see things like the standard error of the mean, this means that 95% of those values in a normal distribution lie between a plus or minus 1.96 standard deviations from the mean. The standard deviation of the sampling distribution of the mean is called the standard error of the mean. And this term error really indicates that when there is a theoretical sampling distribution of the mean, it's used to estimate a population mean. Some error is likely to occur in that estimate just because of the theoretical nature of it. And just because of the numbers of scores you're dealing with. So the smaller the error, the greater the accuracy of the population estimates. Your book will do a little bit of review on that, but just know that sometimes when you're looking at statistical analysis and research, they might, depending on the type and nature, they may mention the sampling distribution of the mean, and it has to do with populations. Okay, statistical inferences have two techniques, and this has to do with estimation of parameters. And I want to talk just for a minute about confidence intervals, because what these are a range of values that with a specified degree of probability is really thought to contain the population mean. For example, in 2004, Tarot and King reported on intradermal injections given with the bevel up versus the bevel down. And what they found was that with the bevel up injection took 4.64 seconds less time than the bevel down. And that occurred with 95% confidence intervals. That every time you use the bevel up, that it occurred in 1.42 to 7.85 seconds. This was the range. So you're going to see confidence intervals given in a range. They have upper and lower limits. Now, I guess they were looking at efficiency for this intradermal injection, but what it says really that the bevel up is the preferred method, and that you can always count on the fact that it will take you 1.42 seconds to 7.85 seconds. Confidence intervals. Don't you love it? So usually you're going to see them reported like a 95% or 99% confidence interval is presented. And it really means that the researcher asserts with some degree of confidence that the population parameter lies within these boundaries. So, wow, let us just say, wow, this study has more generalizability to it. And this is what I just said. This has to do with those confidence intervals. All right, moving on to hypothesis. Remember, hypotheses are a feature of quantitative studies only. And all of these statistics are all about testing this hypothesis. Now, hypotheses are really, everything in a research study is based on, a quantitative research study is based on the hypothesis. And it is either directional, being there's a positive or a negative influence, or that there is no difference, which is the null hypothesis. And really the statistical tests are just set up to test the hypothesis, so that the researcher either accepts the null hypothesis or rejects the null hypothesis. Remember, all inferential statistical tests are based on the assumption that there is no difference, no relationship, or no correlation between variables exist. So, remember that thought, and hopefully this will make sense to you. When you see a research finding that says there is a statistically significant finding, what they're telling you then is that they have rejected the null hypothesis and that there is a difference, a correlation, or a relationship in the variable. Isn't that cool? No significant difference means it really could have happened by chance. There was nothing that happened between these variables, and so then you accept the null hypothesis. Now this is where you're going to see those p-values that we talked about earlier. The most common one used is a p equals 0.05, because the level of significance is really the probability of rejecting a null hypothesis when it is true. You know, our null hypothesis says that there is no difference in IQs with RN to BSN students at UMMC and USM. But our data indicates that if we accept the null, then our data says that there is no difference. But however, when our data comes through, by George, we do have statistical significance. So we reject the null hypothesis to say there is a statistically significant difference in IQ levels in the UMMC RN to BSN versus others. So there we go. The p-value of 0.05 really means that the researcher is willing to risk being wrong 5% of the time, or 5 times out of 100, when rejecting the null. Isn't this great? So there are 2 types of errors. Woo! Type 1, here we go. Rejection of a null hypothesis when it should not be rejected. This type 1 means that the null is right. It is correct. There is no difference. But by George, we've said, yeah, there is a difference. Yeah, we say there's a level of significance when there isn't. That is a type 1 error. Type 2 errors really say that you fail to reject a null when it should be rejected. The null is wrong. The null says there is no difference between these variables, but by George, there is a difference. But we have accepted the null. That is a type 2 error. You control for that by power analysis and by larger samples. So be sure to look for these kind of things when you're reading research articles. See what they say about the stats. All right. Onward to parametric and non-parametric tests. These are 2 types of inferential stats. Remember, we're talking about being concerned with the population. These tests make assumptions about the population from which the sample was drawn. And they use interval and ratio data. Non-parametric stats are really they're less stringent, and they do not make assumptions about the population. These use nominal and ordinal data. and usually are related to a small sample size. So these are two types of inferential stats that you may encounter. Bivariate statistical test. These are the most commonly used in nursing research, and you're going to see these listed in your articles. The t-test, parametric. The ANOVA is parametric. The Pearson's R is both descriptive and inferential. The chi-square is non-parametric. And we've already discussed those correlation coefficients, the Pearson's R. Briefly, t-test. Looking at the differences between two means of two groups of values. Please note, this is one of the most popular. You've got two groups, two means, and you're comparing them. And examines the group differences when the variables are measured at the interval and ratio level of measurement. Put a star by that. The ANOVA. This is whenever the researcher wishes to compare the differences among more than two means. And it allows simultaneous differences between several means to be examined. Excuse me. You're going to see this represented by an F value, like F is in Fred. For example, in my Generation Y and teaching methods research, I had to look at Generation Y, Generation X, and the boomer population means from the questionnaire. And then I looked at each of those items about lecture, case study, online. So I used an ANOVA with repeated measures to look at that data. Cool, huh? Chi-square is a non-parametric inferential technique appropriate for comparing sets of data that are in the form of frequencies or percentages. Most commonly used with nominal data, and it's usually presented as a contingency table. I think about the study that looked at psychiatric nurses smoking more or less than med-surg nurses smoke. And the total sample was 100, but the tables were outlined where they had smokers versus non-smokers, and then psych nurses versus med-surg nurses. And then they also had it broken down into gender. So you're going to see chi-square done in percentages and frequencies, but you're going to see that done a lot. Correlation, we've hit on this earlier, but by George, here it is again. So just remember that you're testing the relationships between two variables, and that it represents magnitude and direction and intensity. Remember, we talked about it being positive or negative. Now, effect size. We talked earlier about the power analysis. Well, power analysis is really a technique that's used to estimate sample size needed to avoid that type 2 error. Remember what type 2 error is. And that if your sample is too small, it makes the data and the researcher accept a null hypothesis that is wrong. It says you're saying there is no difference when there is indeed a difference. So that is the type 2 error, and you conduct a power analysis in order to reduce that chance of type 2 error. Very cool, isn't it? All right. Your book will hopefully give it a little clearer detail. Also include page 238, table 1211 is amazing to help you really digest all of this. Now these multivariate statistical analysis, this is going to be a cursory review because these are considered advanced statistical tests. And this is where you're looking at statistical procedures at 3 or more variables simultaneously. Multiple regression, the ANCOVA, the MANCOVA. And all they're trying to do is explain or predict a dependent variable within multiple independent variables. A study of relationships with several physiological and psychological variables associated with COPD and lung function. You're talking about 20, 30 variables, and then you're going to be applying these multivariate statistical analysis to look at the correlation between all of those. But here's a brief review. The ANCOVA is used when really the researcher wishes to control statistically for some variable that may have an influence on the dependent variable. And as far as Gump would say, that's probably enough for now. I do encourage you to read in your textbook the tips on reading text with stats on page 240. It is fabulous. And remember, the more you do it, the better or the easier it gets. And here we are, hallelujah, at chapter 13. Again, a brief scan because this has to do with the interpretation of quantitative results. Remember that we're not proving but suggesting relationships. Looking at the stats, at the interpretation, you're going to find these in the discussion section. You remember that IMRAD? Well, this is the discussion. Because what will happen is they look at the stats, they make declarative statements or assumptions about the data. They're going to tie it back to the literature that is out there and whether it is supportive or non-supportive or different. And then they're going to make assumptions about how it can be applied to practice. This is all going to be in the interpretation of it. And you will think critically about it as you are reading this article. What about this might you use in your practice? So here's some interpretive tasks as you are reading your research article. So look for the answer. Were the discussion, was the tool, was the statistical analysis, is it credible and accurate? Is there precision to it, magnitude, the meaning? Could you generalize it to other populations? And then what are the implications in practice? So look for them. Also, look at these interpretation of results with an interpretive mindset. Be critical. What did they do wrong? What about the methods? What about the sample selection or the data analysis? Did they do validity and reliability testing on the instrument? And did they identify limitations or extraneous variables? Because you really do want a show-me kind of attitude when you're looking at research. So my goodness, we have covered an awful lot of ground, and you have done so well. I hope you have learned a lot, and as you think about it, and you may have to listen to this again if you can bear up to it, you've learned so much, and you are much more savvy now in thinking about dissecting research. So go forth, nurses, and critique, and we'll see you soon.